CavityRank, a smarter way to insert items into Cuckoo filters. The problem with traditional Cuckoo filters. Cuckoo filters are elegant data structures that answer membership queries quickly and efficiently. They store fingerprints short summaries of items in buckets, with each item having two possible bucket locations. When you insert an item, you place its fingerprint in one of these two buckets. If both buckets are full, you must relocate existing fingerprints to make room. Near full capacity, however, a frustrating problem emerges. A Cuckoo filter may reject a new insertion even though there is technically still space available. The filter could accommodate the item by rearranging existing fingerprints, but the insertion algorithm fails to find this arrangement within its limited search. This happens because standard insertion policies follow a blind, indirect path. They randomly kick out fingerprints without any sense of direction, often revisiting the same full buckets repeatedly. The two extremes, blind guessing versus exhaustive search. Existing solutions sit at two uncomfortable extremes. Random eviction kicks out a fingerprint and follows a single path, but it lacks any persistent direction. It stumbles around without remembering where a free slot might be. It's cheap to compute but frequently fails when the table is nearly full. At the opposite end, breadth-first search methodically explores all possible relocation paths by maintaining a growing frontier of buckets to examine. This approach finds successful paths more reliably but requires significant memory storing parent pointers and visited states proportional to the entire table size. It's powerful but expensive. The missing design point is a middle ground, a guided single path that retains some directional information without expanding the bucket representation or adding auxiliary data structures. The key insight: order matters. The clever observation behind CavityRank is that a full bucket containing 4 fingerprints has 2 distinct views. When you query whether a fingerprint exists in the bucket, you only care about the set of fingerprints present. Their order doesn't matter. However, when you're inserting items, you can use that order as hidden information. Specifically, a full bucket can arrange its 4 fingerprints in different permutations. Since lookup treats all permutations as equivalent, these different arrangements can carry extra information without affecting correctness or memory footprint. CavityRank exploits this by encoding a small rank value in the lane order of each full bucket. Using just 2 comparison bits, whether the first pair of fingerprints is in a particular order and whether the second pair is, CavityRank stores a 4-level ordinal rank. This rank tells the insertion algorithm something about how close each bucket is to finding a free slot. The beauty is that this information comes at 0 extra cost. The bucket remains exactly 64 bits, the same as before. How guided routing works. When an insertion encounters a full bucket, CavityRank examines the 4 possible fingerprints it could evict. For each candidate, it looks at the destination bucket and checks its rank. It then chooses the fingerprint whose destination has the lowest rank, effectively moving toward buckets that have previously shown promise. This is a minimum rank single path approach. The algorithm follows one relocation path, but unlike random eviction, it persistently moves toward lower ranked buckets. The rank acts as a directional signal, gradually steering the insertion toward a cavity. After relocating a fingerprint, CavityRank updates the rank of the modified bucket based on its new outgoing edges. This is crucial. The rank reflects the graph that actually exists after relocation, not what was there before. The algorithm recomputes the rank from the bucket's current fingerprint arrangement and encodes it in the lane order. This creates a feedback loop. Each bucket's order encodes information about the quality of its outgoing edges, insertion follows better paths, and after each modification the rank is refreshed to maintain accurate guidance. Measuring success, separating capacity from search. One of the paper's important contributions is distinguishing between two types of failure. An insertion might fail because the table is genuinely full, there's no possible arrangement that accommodates all items. Or it might fail because the bounded search policy simply couldn't find the arrangement that does exist. To separate these, the authors use an exact oracle that performs an exhaustive search to determine whether a given prefix of items is structurally feasible. By comparing online policies against this oracle, they can measure how much of the search gap each policy closes, the difference between what the oracle can achieve and what the limited policy can find. This careful measurement reveals CavityRank's effectiveness. In one key experiment with a 4096 bucket table, random Cuckoo filtering fails about 33 items before the oracle would be forced to stop. With just one hidden bit CR2, this gap shrinks to about 4.5 items, an 86.5% improvement. With the full 2-bit 4-level rank CavityRank, it shrinks further to just 0.46 items, meaning the policy is nearly as effective as the optimal oracle. Performance in practice. The paper presents detailed measurements of CavityRank's performance in a real implementation. At a high load of 97.75%, CavityRank uses about 42.5 logical reads per insertion. By contrast, using explicit labels to guide insertion requires about 62.7 reads, and a depth-limited breadth-first search needs roughly 356 reads. CavityRank thus reduces memory traffic by 32% compared to labels and 88% compared to BFS. Moreover, CavityRank requires no extra persistent memory. The control information lives entirely in the lane order of existing buckets. It also needs no table-scaled workspace for searches, unlike BFS, which must allocate parent and visited structures proportional to the table size. Why it works: ordinal ranks, not exact distances. The rank system uses only 4 levels, not exact distances to the nearest cavity. This simplicity is deliberate. It's a local signal that tells the algorithm which neighboring buckets have lower ranks, providing a kind of gradient to follow. The limited range keeps the encoding small, just 2 bits per full bucket, and avoids the need for table-wide consistency. Think of it as a signpost rather than a GPS. It points in generally promising directions without calculating exact route lengths. This trade-off, less precision for zero extra memory, proves remarkably effective at eliminating most of the search gap. Broader implications. CavityRank demonstrates a more general principle: data structure representations often have unused degrees of freedom that can carry control information. Whenever a query observes an equivalence class rather than a unique representation, those degrees of freedom are available for auxiliary purposes. This insight extends beyond Cuckoo filters to other data structures where the same logical information can be represented in multiple ways. The algorithm occupies a practical middle ground between expensive exhaustive search and cheap but aimless random kicking. It demonstrates that a small amount of persistent directional information stored at zero cost in the bucket order can dramatically improve insertion success rates near capacity without sacrificing the compact representation that makes Cuckoo filters attractive in the first place. For applications where memory is precious and insertions happen frequently at high load, CavityRank offers an attractive design point: guided enough to recover most of the capacity gap, compact enough to preserve the packed representation, and simple enough to implement without complex auxiliary structures.